So you may recall from chapter 3, we talked a little bit about even and odd functions. So recall that an even function means that if you plug in a negative input, it gives you the same output as if you had plugged in a positive input. In other words, the sign of the input does not affect the output. So other even functions that we've talked about are x squared. So why is x squared an even function? Because you get the same thing whether you plug in positive x squared or negative x squared. So how about odd functions? In an odd function, when you plug in a negative input, it gives you the same output, but a negative output. So, for example, functions that we've looked at that were odd functions were x cubed. When you cube x, it's negative if you plug in negative x. So now we want to evaluate sine, cosine, tangent, cotangent, cosecant, and secant to see if they are even or odd. So remember that when we're working in the first quadrant, we have positive cosine and we had a positive sine. When we worked in the second quadrant, we had a negative cosine, but we had a positive sine. When we work in the third quadrant, we have negative cosine and negative sine. And when we work in the fourth quadrant, we have a positive cosine but a negative sine. So what does that really tell us about whether something's even or odd? So remember, this is a positive angle going this way. This is a negative angle going this way. So look what happened to the cosine when we plugged in a positive angle. Positive cosine. Look what happened when we plug in a negative angle. We still get a positive cosine. What that means is that the cosine is the only even function. In other words, the cosine of a positive angle is x. The cosine of a negative angle was still x, right? In other words, it didn't matter if we plugged in a positive or negative angle. And because the secant is the reciprocal of the cosine, the secant is also even. Now, everything else, when you plug in a negative angle, becomes negative. So now let's look at the sine. If I have a positive angle, I have a positive sine. But as soon as I come backward and have a negative angle, notice that I had a negative sine. So the sine is odd because the sine of positive theta is y, and the sine of negative theta is negative y. The same is true for the cosecant, the reciprocal of the sine, and for the tangent and for the cotangent. When you plug in a negative angle, you get a negative output. So that is what we mean by even and odd. So this guy's even, cosine is even, right? This guy's even. What that means is that I can ignore the fact that there's a negative angle, because the cosine of negative pi over 4 should be the same as the cosine of positive pi over 4, right? Which is 45 degrees, so I get 1 over root 2. Same thing for the secant, right? So the secant of negative pi over 4 is the same thing as the secant of positive pi over 4, which is the reciprocal of the cosine of pi over 4, and I get root 2. Okay, so I can completely ignore the fact that the angles are negative because they are even functions. For the odd functions, okay, these are the odd functions, it means that as soon as you plug in a negative value for the angle, it makes the output negative. So this is going to be the same as negative tangent of pi over 4. So if you know the tangent of pi over 4, or the tangent of 45 degrees, is equal to 1, that makes this equal to negative 1. Sine of negative pi over 4 is the same as minus the sine of pi over 4. So again, if you know the sine of pi over 4, or 45 degrees, is 1 over root 2, then this will be equal to minus 1 over root 2. One other thing that helps us when we work with trigonometry are identities. Identities are equations which are true for all values of x, or in this case, theta. Okay. You've used identities a lot in Algebra 1. For instance, you probably recognize this identity. If you have x squared minus 1, you may rewrite it as x minus 1 times x positive 1. It's basically just a rule that shows us equivalent expressions. So we've talked about these a little bit already when we defined the cosecant, secant, and cotangent, but let's start off by looking at what we call reciprocal identities. The reciprocal identities tell us that the cosine is the reciprocal of the sine, and the sine is the reciprocal of the cosecant. We know that the secant is the reciprocal of the cosine, and the cosine is the reciprocal of the secant. We know the cotangent is the reciprocal of the tangent, and the tangent is the reciprocal of the cotangent. So, we also want to look at another set of identities which are called quotient identities. Remember, the word quotient means division. This tells us that we can rewrite the tangent, which we know to be equal to y over x, as sine theta over cosine theta. This is true because we know that the sine of the angle will always give us the y value, and the cosine of the angle will always give us the x value. Of course, if the tangent is equal to sine theta over cosine theta, then its reciprocal, the cosine, will be equal to cosine theta over sine theta. So why do I want to learn all these identities? It actually saves me a tremendous amount of work, because if I'm given a little bit of information, like I am over here in example 4, I can use that information to solve for other trigonometric ratios. For instance, how do I find the tangent if I'm given the sine and the cosine? Well, I know that the tangent is going to be equal to the sine divided by the cosine. Therefore, the tangent will just be equal to 2 over root 21. If I know that the cosecant is merely the reciprocal of the sine, and the sine is 2/5, that makes the cosecant 5/2, right? In other words, it's the reciprocal of the sine. If I know the secant is the reciprocal of the cosine, then the secant must be 5 over root 21. In other words, it's 1 over the cosine, or the reciprocal of the cosine. Lastly, I can find the cotangent by looking at the reciprocal of the tangent. So this one will be root 21 over 2. In other words, I can take a little bit of known information and I can use it to find lots of other new things that I might be looking for, other trig ratios. All right, the last thing we're going to look at is a couple other Pythagorean identities. And these are based on the Pythagorean theorem as per their name. Okay. So last time we were talking about the unit circle, we were saying that the cosine of theta was x and the sine of theta was y. But if we look at this triangle right here, we know from the Pythagorean identity that x squared plus y squared equals 1 squared. Now, if you just replace cosine theta with x and sine theta for y, you get this expression. Cosine squared theta plus sine squared theta equals 1. This is what's known as the Pythagorean identity. It shows that there's a relationship between the cosine and the sine. We can use this Pythagorean identity to solve for other Pythagorean identities. Start with the original Pythagorean identity. Divide both sides by cosine squared theta. Now you can simplify this expression by applying the reciprocal and the quotient identities. Obviously, cosine divided by itself is equal to 1. Sine squared over cosine squared is going to be equal to tangent squared. And 1 over cosine, applying the reciprocal function, is 1 over cosecant squared theta. We could do the exact same thing on the other side. Start with the original Pythagorean identity. This time, instead of dividing dividing every term by cosine squared theta, I'm going to divide every term by sine squared theta. And then again, I'm going to simplify this, right? So cosine squared theta over sine squared theta was cotangent squared theta. Sine squared theta divided by itself is 1. And the reciprocal of the sine, or 1 over sine, is, oops, I have a mistake on mine. This should say secant. Let's fix this one. This one should say secant. Secant squared theta, there we go. And this one is the cosecant. So, again, you can use these to solve a problem. If I know the sine is 3 over 5, I can plug that into the Pythagorean identity, and I can solve for the cosine. Cosine squared theta plus sine squared theta, right? In other words, 3 squared over 5 squared equals 1, and I can solve this equation for cosine squared theta. All right, the last identities we want to look at are the periodic identities. Okay. Periodic functions are functions that have output that repeats over a given interval, and this given interval is what we call the period, right? How often does it repeat? Okay. So, the interval over which it takes to complete one cycle, right? In other words, how often before it starts to repeat. So the sine is going to repeat every 2 pi, right? In other words, one rotation around the circle, okay? And the cosine is going to repeat every 2 pi. So both of these repeat after one full rotation around the circle. The tangent, however, is a little different. The tangent repeats over pi. In other words, the tangent repeats over half a circle. The reason why the tangent repeats is because remember that the tangent is the slope. So, that means that if I want to find the sine of 9 pi over 4, I can rewrite this as the sine of 2 pi plus the sine of pi over 4. Since this is just a full rotation, that means that the sine of 9 pi over 4 is the same as the sine of pi over 4, since these are coterminal. So the sine of pi over 4 is equal to 1 over root 2. Let's look at the tangent. The tangent minus 5 pi over 4 is here. Right, go move backward. So this is the same thing as the tangent of minus pi